It's pretty easy to get confused. They're very, very similar, in fact. There's very little difference, but there is a very important key difference here. Okay, folks. If we're looking at these oxidation states, right? Whenever we did oxidation numbers, how did we split up the electrons in a bond? We always just counted half the number of electrons in a bond. Didn't matter if it was electronegative or not, right? Okay. This time we're doing oxidation states, so if we're bonded to something more electronegative, then the electrons are going to go to that one, okay? If we're bonded to something less electronegative, the electrons are going to get taken from that less electronegative species, right? So right here we see an example with the totals in it. So right here we have a carbon-carbon bond, and so we split that in half. Neither is going to be able to successfully take the electrons from the other, and that's a more or less nonpolar bond, right? Over here we have a pretty polar bond, don't we? And that's that carbon-oxygen one. And so what's going to happen here is all four of those electrons that are in that double bond there, they're all going to be assigned to the oxygen. They're not going to be assigned to the carbon. Okay? And that's because the oxygen is more electronegative, right? Now, in reality, these would have partial charges, right? Not full charges like we're going to represent here. But these full charges we're representing here are just a representation of what sort of oxidation numbers you're looking at in terms of like oxidation state. Okay? It's a good way to determine whether something is reduced or oxidized, which is what we're focusing on here, right? So a quick calculation you can make to determine oxidation, whether something's reduced or whether it's oxidized. Okay, so let's look at this species right here. We had a reaction. We'd go ahead and look at the oxidation state for this carbon here. And we're trying to figure out, is that one oxidized or is it reduced? Okay. And so we again look at here. We have a carbon-carbon bond, and so we're going to get 2 electrons in each of those, aren't we? Okay. We're going to get 0 electrons being contributed from this more electronegative species being bonded. Okay. The oxygen's going to take electrons, right? All right. And so we look at that carbon, and it only has 2 electrons assigned to it. We look up the valence shell, and how many electrons should carbon normally have? 4. And so it's at +2, isn't it? Okay? And so the oxidation state, +2. We look over here, and now we have a carbon-carbon bond, right? And we have another carbon-carbon bond, same as before. And so those are going to get 1 of those electrons each. Is that making sense so far? Fantastic. Right here we have the 2 electrons in this bond to the oxygen. Those are going to go to the oxygen because that's more electronegative. Those electrons are going to spend more time on the oxygen. Over here we have a hydrogen. Hydrogen is less electronegative than that carbon, and so those electrons are going to spend more time on the carbon, aren't they? Okay. And so the oxidation state for this one is going to be 0. And we look at the oxidation state. It decreased. And so what do we call that? That is a reduction, right? We reduce the number, so it's a reduction, isn't it? Okay. If the number goes up, that's going to be an oxidation. Exactly. Okay. All right. So right here we can see some more examples. So here we have a catalytic hydrogenation, right? And notice we're going to take that double bond. We're going to add across it, and that's going to give us our alkane, isn't it? Okay. And so what sort of reaction is that? That carbon, is it being oxidized or reduced here? It's reduced, right? Yeah. So this is a reduction of that carbon, isn't it? Both these carbons, in fact, are being reduced. Okay. What's being oxidized, by the way? If something's reduced, something else has to get oxidized, right? That's why it's redox. They're always together, aren't they? And so, what's being oxidized in this reaction? The hydrogens. You got it. Yep. The hydrogens were zeros, right? Because they're bonded to the same thing. Now they have the 2 electrons being pulled from them by the carbon, don't they? Okay. Note that please don't get these confused with oxidation numbers. They are very, very different, right? This carbon here has a -2 oxidation state, right? Does a carbon have a -2 charge here? No. These are going to be stupidly large numbers if you take them to be like oxidation numbers, right? That these are the actual charges on these things. Okay? What they're going to be is a nice tallying you can do very quickly. Okay? Instead of the reality here being this is like a 0.2 charge. Okay? Yeah. That would be actually pretty drastic. Is that making sense? Okay, let's talk about poisoned catalysts. So here we have, again, that hydrogenation. And what we're going to do here is so we can better control this hydrogenation so we don't get complete hydrogenation all the way down to the single bond, we're going to do what's called poison our catalyst. Okay? What is a poison catalyst going to mean? It's slower, exactly. We're inhibiting in some way. Catalysts theoretically should not break down. That's what makes them catalysts. In reality, they actually do break down slowly. And what actually happens to most catalysts is they become poison catalysts, actually. So if you did the natural corrosion to most catalysts, they'd actually get inhibited slightly as you go along. And they would actually become poison catalysts over time, usually. But this is very specifically controlling this catalyst reactivity. And so we're reducing the reactivity of that catalyst, how much it's going to reduce the activation energy, right? We're limiting that so that this reaction doesn't go as quickly. And so we can actually collect this double bonded form rather than it going immediately to the triple bond. Okay. All right, so again, that's a poison catalyst. We will only get the cis isomer. Does anybody know why we only get the cis isomer? For hydrogenation. That's not about stability, actually, in this case. It's not really a kinetics or stability thing in this case. Location. Yes, but location of what? Nobody remembers this one? Ooh. Oh my goodness. Uh-oh. This is like the stereotypical addition reaction, everybody. Specifically, you have these H's coming in on the same side, don't you? These hydrogens are connected. So they end up coming on the same side, and they always have to attack from the same side, and so the hydrogens are always on the same side. Which is cis, isn't it? Okay. So let's talk a bit about who here's taking the MCAT, by the way, or any testing to go in like pharmaceutical school, any of that. Okay. Review. It depends on the year, but organic chemistry tends to be about equal to like the biochemistry. And altogether, biochemistry and organic chemistry tend to be the largest sections of those exams. Okay. Also, it's the number one reasons to fail out of the PA school or medical school or any of those. And it's because if you don't use the stuff after a week or two, it disappears, right? And then you got to relearn. But it is easier to relearn. Okay, so this again is going to be various different reductions of different functional groups. In this case, we're going to use catalytic hydrogenation. Catalytic hydrogenation just meaning you're doing hydrogenation with the gas here and the presence of a catalyst. Right. Same process that makes peanut butter, in case you're wondering. Okay. I know. You have to use peanut butter as the example. Everybody loves peanut butter, right? Yeah. This one's aldehyde. This one's a ketone, of course. This aldehyde is going to give you a primary alcohol because it's at the end there. This ketone has to give you a secondary alcohol because that gives you 4 bonds from a carbon. Nitrile, right here, is going to go to a primary amine because you're going to reduce that twice. so that you get rid of the double and the triple bond. Please note that you can actually limit this with a poison catalyst, and you could get the double bond. It takes a little tinkering, but you can do it. Okay. This is going to be your primary amide. Everybody recognize amides? Like proteins, right? Okay. Yeah. That's the amide linkage in a protein. And again, this is going to be reduction of it. That's going to give you a primary amine, actually, because this is actually going to reduce this bond right here all the way down on that spot. These are very analogous to carboxylic acids, okay? And that's actually what you're seeing here is that amides are actually considered one of the more reactive carboxylic acid like compounds, okay? They oftentimes are actually grouped up together because they do a lot of the same reactions. So again, this is going to be your catalytic hydrogenation. It's going to selectively reduce the alkene's double bond here to a ketone. So if you undergo selective catalytic hydrogenation here, this conjugated form is actually going to reduce first. This is, again, that same. This one's that kinetic thermo control that you guys were thinking of. Same thing. So right here, if you were to do liminin, this one here is going to be the one that's going to reduce first. It depends on how much of this hydrogen you have, by the way. If you put 2 equivalents of hydrogen in, you can end up reducing everything down, of course. But kinetically speaking, this one's going first. And this more exposed one is the one that's going to go first in this one. Okay. Notice you get excellent yields for this. This is one of those reasons that catalytic hydrogenation is one of the most common reactions done in industry, because the yields are amazing, and industrial machines actually make this incredibly easy to do. Yeah. Not easy to do in labs, because we're always having to tear our equipment down so it leaks the gas, right? But in something you can just leave and just check and make sure it's always set up properly, and you can have a monitor on it, gas reactions are actually really easy to do. So this is your Wolff-Kishner reaction right here. So this was section 19.6, if you don't remember very well. And this one here was the carbonyl of your ketone or aldehyde. And we are converting it to a methylene using this diazo compound here. Okay. And so this one here is, again, a reduction, isn't it? We're reducing down that ketone or aldehyde down to a CH2. Okay. This is the Clemmensen reaction. This one is the one from shoot, I didn't put in my notes where exactly it comes from. It was one of the previous chapters, though, that we did this semester, actually. The Clemmensen reaction. So this is actually a Clemmensen reduction specifically. It's going to use zinc amalgam. This is zinc amalgam. It's where you take mercury and zinc and you amalgamate them. Does anybody know what an amalgam is, or amalgamate? No. You melt them together so they're a single solid. Okay. It's not the same as an alloy, though, because they're not mixed as thoroughly. Okay. So they actually will have spots. Anyways, this is in the presence of HCl. It's going to be water, reflux it for 5 to 8 hours. And so what you're going to do, it's again going to be an alloy, a blend of this, but amalgams typically are made of very specific metals, and they're a very special form of these blends. They actually typically have some more exposed regions that you can see some different crystal structures, but I'm not going to go into that. Because, as my inorganic class can attest, crystal structures are wonderful, right? Okay. Okay. Anyways. This one here is going to have this, the ketone or aldehyde in this reflux here is going to continually be evaporated and reconduced under the heat. And this amalgam is going to be in concentrated HCl. You'll notice this is very similar to some of the reactions we've done before. It's just we're using a metal catalyst in this case. So again, this is going to be another reduction. So we're reducing this carbon right here. Your zinc here is actually your reducing agent. So I'm sorry, I said catalyst, but it's not catalyst. I got up really early today. Yeah, probably should have drank some more coffee before I came in. Anyways, this is actually the one that gets oxidized right here, which is your zinc. Okay. Actually, normally when you see zinc, it is a reducing agent. It's something that's providing your electrons. Okay. Similar as when you used magnesium and lithium in your previous organometallic reactions. It was a electron source. This specifically has kind of an interesting name, and that's because it's typically called the dissolving metal reduction. And what's happening here is you put this in the HCl, and the metal's actually going to dissolve as you go along in this reaction. Okay? Okay. You can think of it a bit like making your hydrogen in solution, if you'd like. This right here is the Raney nickel reduction, actually. So this is going to be reducing carbonyl right here. First to a thioacetyl, and then you're going to reduce it further with Raney nickel, which is in hydrogen, down to the methylene right here, the carbon hydrogens, 2 hydrogens. This, by the way, is actually a valid methodology for doing a protecting group under certain conditions, in case you're wondering. So you can actually do this first as a protecting group, and you can actually take this group back off and reduce it, oxidize it back instead. This is just another way you can go in it, which is the Raney nickel one. Okay. Is there anything else I need to add to that one? So this right here is both the hydrogen source right here, and so it's also going to be your nickel here. And what we do to get this nickel here, Raney nickel, is we take 50-50 alloy of aluminum nickel, and we put hot NaOH with it. And this is actually going to etch your metal. And so, by the way, you can etch metal with NaOH, hot NaOH, especially if it's reactive, like an aluminum nickel source. And so you can actually etch designs on these if you ever want to do that. This actually is kind of interesting because what's going to end up happening here is you're actually going to make like this bubbled up metal structure, and it's going to trap the hydrogen inside of it. Did anybody ever do a loom reaction back when they were young and chemists? No? No? Dang. So that's actually where you take aluminum and potassium hydroxide, and you put them together and you heat them, and it dissolves the aluminum, actually. And what you end up getting is you evolve hydrogen gas. So the nickel here's purpose is actually 50-50 nickel aluminum. It swells up the nickel structure around the hydrogen gas, and then you're going to have nickel hydrogen gas sponge, essentially. Okay? That you're then going to put this in with, and it's going to react. Keep in mind, there's kind of an interesting side effect to this, is that number one, you're using a gas here, but it's not really in gaseous form, right? So that's kind of interesting. The other interesting side effect to this is that because it has a sponge-like structure, it actually has a huge amount of surface area to do this reaction. So it's much faster than you might think. Okay. This is actually also the catalyst, by the way, the nickel here in this reaction. In this case, it's not actually the electron source, which was actually the aluminum in this case, right here. Okay, so which reduction reactions or reaction, the Wolff, Kirchner, Clemenson, or Raney nickel, can be used to carry out the following transformation right here? So which one would be an appropriate one to use in this case? Okay. So what I want you to do is write down your guess. Okay. Everybody write down your guess here. And then if you get it wrong, you gotta do some extra homeworks. The examples in your book of this, okay? Yeah. I know, high stakes one. Yep. You guys know the examples in your book, right? Little test yourself things that you can. Yeah. Okay. Gotta do 3 extras. Let's make this real painful. And if you get it wrong and you don't do it or don't even guess, then you can know that that's just pathetic. And I won't know, nobody else will know, but guess what? You'll know. And you'll go, damn, that was sad. You can discuss with people next to you. Try to hash it out, get a little arguments, getting passionate about it. Rennie nickel! It can only be Rennie nickel. Because why? Because I love that one. It's just awesome. It's so clever. In case you're wondering, I've been working since like 5 something in the morning. So, only thing keeping me awake right now is coffee. Okay, folks, let's go and go forward. Everybody got your answer written down? Okay, ready for it? Find out if you have to do that extra homework. I don't know. Okay. So, right here we have this carbonyl we need to reduce down, right? And it's a ketone in this case. We want to get it all the way down to the methylene group. We do have some problems here. We don't want to have that carbon bromine being reacted away. We also have another problem, which is that, yeah, aromatics are stable, but they're still double bonds, right? So if we get this reaction going, if we really get it going enough and it's a powerful enough reducing agent, those will react, okay? And so we could react away the aromatic rings. We need to watch out for that. Okay. And so let's think about the conditions for the Wolff-Kishner reaction first, okay? So our conditions are hydroxide and hydrazine here, okay? These are both nucleophiles, and so if we add those in with carbon bromine, that's going to be a good site to react nucleophiles, right? Really good leaving group. And so we'd actually end up doing the SN2 reaction. And we get attacks on this site, and we wouldn't have the bromide still there. It would also give us this part here. That's no problem. But, yeah, we wouldn't have that bromide still there, would we? And so that's a big problem. It's probably not the answer we would want. So let's talk about the Clemmensen reduction here. So the carbon bromide group nor the aromatic rings are going to be susceptible to reaction with carbon HCl, the chloride here. It's not a particularly good nucleophile. It's a very poor one. And so the likelihood we get any real substitution happening here is very low. Okay? At least not in the time period we would need to do the Clemmensen reduction. So that one works. If anybody got the Clemmensen reduction and that was your choice, congratulations. You're good. You don't have to do any extras. Fantastic. Very good job. Let's talk about the Rennie nickel one. So the alkene would be reduced under catalytic hydrogenation conditions, which are our H2 and nickel. You may have noticed that that's actually very similar. The Rennie nickel conditions are very similar. It's actually just using a nickel catalyst for the hydrogenation. It's just a much more elegant way to do it on a smaller scale. Okay, where you'd be in like a lab and you'll have gas that you can evolve for heat pressure and all that. So it's just kind of a neat way to do that. The aromatic rings are going to be unreactive. However, we do have a problem here in that one of the conditions, which is the thiol condition, actually is a nucleophilic and can cause SN2 reactions. And so we would again get a little bit of reaction with that CBr group from the thiol step, actually, not from the Raney nickel step itself. It's the setup step that's going to get us problems. Okay? So if you guess the Raney nickel condition, you got to do at least 2 problems. Okay? It's I get why you might have guessed that one. But you got to do at least 2. Okay? You can do the full 3 if you want to really feel like, yeah, fulfilled the oath there. Okay. Everybody good? Okay. All right. So let's talk about some limitations now that we've tested our understandings of these a little bit. So the Wolff-Kishner reduction should be avoided if a functional group is going to be present that's susceptible to reaction under basic conditions or with strong nucleophiles. It has both. It has a pretty strong nucleophile, but also a strong base, right? And so anything that reacts under those 2 conditions is going to react in this Wolff-Kishner reduction, and you're going to end up reacting those as well. The Clemmensen reduction should be avoided if your functional group is going to be present that's susceptible to reaction under acidic conditions. So if you remember, your Clemmensen reduction up here had the presence of HCl, right? So anything that reacts under acidic conditions is going to be an issue. For example, if you have something that can react because you made your alcohol a better leaving group, that's going to be a problem, right? If you have something that's going to react because you can add those across, that can be a bit of an issue. Okay, so watch out for that acidic condition. The Raney nickel reductions should be avoided if a functional group is going to be present that's susceptible to 2 major things. That's nucleophilic thiols. Now, nucleophilic thiols are not exactly amazing nucleophiles, but they are nucleophiles. Okay, so if you have a pretty good leaving group, that's going to be an issue. H2 in the presence of a metal catalyst also has the same limitations for the Raney nickel. It is H2 in the presence of a metal catalyst. It's basically a hydrogenation, but in a special way. Okay? In a more limited way. So it has a lot of the limitations that hydrogenation would have. Let's talk about some oxidations. Specifically, we're going to be looking more at alcohols and aldehydes for now. So here's chromium trioxide in the presence of water and sulfuric acid. This is going to make chromic acid. Chromic acid is very, very reactive. Be very careful with it if you actually ever do this, okay? There's actually a variety of uses for it. For example, you can use it to etch. You can use it to make like really cool designs on metals and stuff. It's one of the ways they do that. It also can be used to clean instruments sometimes if you have something extremely aggressive. An interesting side note is there actually are types of microorganisms that can actually live in chromic acid. And so you actually always have to make fresh chromic acid all the time if you use it. But there's a lot of things that dissolve in chromic acid that don't dissolve in almost anything else. So it's very useful. So the oxidation state of the CR here is going to be +6. It's very, very oxidized. The sodium dichromate here can also be used to make chromic acid. Has anybody ever heard of hexachromium, by the way? No, has anybody ever heard of chromium? Yeah, so chromium actually is necessary in your diet. So there's anybody ever heard of Aaron Brockovich? So this was one of like the textbook evil corporation killing people and then being evil about it. Okay? Like if you look at any environmental pollution thing and you want to see an example of like a corporation just being downright wicked and evil, this is the one, okay? There's actually a pretty good movie. It's Aaron Brockovich, it's the movie. She was a paralegal she and a lawyer went and they saw a bunch of people were dying from a variety of different diseases in this town. It was a small town, but they had something like 400 people sick, 200 people had died. Okay? And so they started looking back, what the heck's going on here? And what they ended up finding out is, I kind of started at the end here, but the corporation had a leak. Okay? And so they leaked chromium into the water supply for the town. That chromium, hexachromium, is highly, highly toxic. If you ever want to see what it does to an environment over a long period of time, look up Tamil Nadu. Okay? It can be used to tan leather. And so that's what they do at Tamil Nadu. And they have wiped out almost all the environment for miles around. Nothing grows. It's just completely toxic. Okay? It can cause a tremendous number of problems in humans, from leukemias, different cancers, to everything else. It's pretty wild, actually. Very, very toxic. However, chromium 3+ is a necessary nutrient in your diet. You have to eat chromium 3+. So what the corporation did is, when they had the leak, there's a statute of limitations on all lawsuits, they told the town that we leaked chromium 3+ into your water. Oh, don't worry, it's a nutrient. It's not going to hurt anybody. And in fact, they had leaked chromium 6+ in their water. And they actually were within a couple of years of that being out beyond the statute of limitations. Killed hundreds of children. Like, really, really, really fucking evil. And all the people would have had to do is not drink the damn water. Like, that's it. And they would have been saved. If they had just known. Really evil. Interesting side note to this story is the lawyer in that case did it pro bono. So he was a real big hero at the time, and has been a big hero for a long time. It recently came out over like the last year and a half, I think it was ago. It might have only been a year ago, though. Feels like it's been a long time. That guy was actually embezzling funds from later cases. So, not that case, but he had a history of embezzling funds, apparently, and he's went to jail now. So, hero one day, villain the next. I don't know what to tell you there. But it's actually a pretty landmark case of like a really, really, really evil corporation. Typically, corporations are not quite that evil because they don't have the military to back it up. So they can never get like SSR, Valley of Death evil. So, but that case they did. So a second-degree alcohol, this is going to be your cyclooctanol in this case right here. We put it with chromic acid, and this is a very powerful oxidizing agent because that chromium right here has such a large charge on it. And this is actually going to give you the ketone. It's kind of interesting because, again, right here we have this very flexible oxidizing agent, in fact. This chromic acid oxidation is also commonly called a Jones oxidation, because there's a history where the person that invented this was Sir Edward Jones, which is actually relatively only died 2002, in case you're wondering. But yeah. Right here's the mechanism, and so the first what's going to happen is we're going to put it with the chromic acid here. And the first thing is that the first hydrogen here is going to be removed. And so you're going to get several steps where the hydrogen is removed, and then the chromium actually binds to this oxygen. And that's going to generate this leaving group right here. And so this is actually going to end up being your leaving group. This is actually going to stabilize that negative charge on this resonance structure centered around chromium. Isn't that kind of neat? Notice it looks a lot like a phosphate, doesn't it? Actually has very similar structure patterns, phosphates, resonance structure pattern. What's then going to happen is the second hydrogen is removed, actually. This is done by water. The chromic acid is typically it's a water-soluble acid, so it's typically in water. Notice that this is an E2 reaction. And we're going to get that elimination product which is the carbonyl here. Anybody have any questions so far? Okay. All right. Let's talk a bit about some requirements for oxidation. So tertiary alcohols are not going to be oxidized when treated with chromic acid because we don't have any hydrogen atom right there. So you can't do that second part of this mechanism. So you could form this structure right here. But you can't leave because you can't pull the electrons in to make that second bond. The carbon is too stable. You need a hydrogen to do that. So you'll get no oxidation here. That leaving group's just going to leave, and you'll go backwards in the reaction back to here. So notice an equilibrium here. Right. So the primary alcohol here is going to be oxidized all the way down to a carboxylic acid. So if instead you had a primary alcohol here, what you're going to see is it's instead going to do this reaction over and over and over until you get the oxidized state, the most oxidized state, which is going to be this carboxylic acid right here, without breaking the carbon-carbon bond. That is. And so what you see here is the first thing you're going to do here is you'll do the chromic acid. That will give you the carbonyl here. It is an aldehyde. Notice that you actually have water in the presence of an acid, right? And so then it's going to react, that aldehyde, and give you the aldehyde hydrate right there. That frees up, again, a hydrogen and your alcohol here, either one, doesn't really actually matter. And then this chromic acid is going to do that reaction again, where it eliminates this hydrogen and one of the hydrogens on the alcohol, giving you the carbonyl again. And so that's going to oxidize that all the way to a carboxylic acid. You'll notice that carboxylic acids were one of those very reactive groups we had talked about in the last year that we've been talking about reactions, that you can do a variety of different things with. For example, you can make amides, right? I know, we're wrapping all these back around, aren't we? Uh-oh. This is going to be your pyridinium chlorochromate. This is PCC right here. And so this is going to actually be used to oxidize a primary alcohol to an aldehyde, and a secondary alcohol is going to go to a ketone. And notice that this is more moderate conditions than the chromic acid, so you're not going to do it over and over and over. You'll just get a primary alcohol down to an aldehyde and stop there. No carboxylic acid. Okay? All right. Oh, also notice that this is not water, right? So this aldehyde has no water to react with. This is a non-aqueous. You can do this in a non-aqueous solvent. Okay? That's one of the key things here, is that not having the water to be able to go to the alcohol, right? To add that OH on. Okay, so let's show out how to carry out the following synthesis. Again, it's an honor methodology, so try out this reaction, do your best you can. If you can't make a good amount of progress to it, then it's something you want to go back and study, isn't it? Because it means if I have to be the one to answer this, I don't really know it yet. Then admittedly, you have to practice prompts anyways, because it's called homework. But at least show you, hey, you might want to focus on that one a bit. All right. I'm going to go ahead and start moving forward. Hopefully you made some pretty decent progress on it. Okay. So I'm going to do a retrosynthetic because we have our final product. And going backwards is always the easier way to do that. And so the first thing I'm going to do is I'm going to undo my oxidation because it's actually easier to attack a carbonyl and go to an alcohol and then come back than it is easier to do most of the other ways of doing this. So I undo the oxidation with one of the oxidation methodologies I just talked about. For example, we can use PCC. That would be a good one since we just talked about that slide before. So this would be the bond that I'm going to break right here. It's going to be that bond next to where the carbonyl would be, i.e. where the alcohol is in this one, right here. Okay. I'm going to do it on this side because putting together the benzene ring portion of this would be much harder to do. The benzene ring is much more stable, right? So we would need much more energetic conditions to mess with that. This one's easier. The thing I'm going to go with is I'm going to go Grignard reagent. Okay? Because it's the one you guys have seen the most, right? Sure. And so I'm going to take this chain here. On this side here, it's going to have the Grignard reagent right there. And so that's my Grignard reagent. I'm adding this chain. That is going to right there be the carbonyl, where I'll be attacking with that electronegative carbon right here. Okay. All right, let's go ahead and flip this around and look at the reaction conditions then. Okay, and so if I have an alcohol, the first thing I can do is I can go ahead and use PCC. It's a primary alcohol. It would give me the carbonyl right here, right? Once I have a carbonyl, I can just do the Grignard reagents like we talked about in the previous chapters, where we were attacking the polar double bonds, right? And this is the reaction conditions for that Grignard reagent. Finish this up. Notice it's the presence of a very weak acid and water. Give me the alcohol here. And the next thing I can do is I could use either, by the way. I could use PCC or chromic acid. In this case, I'm going to just go ahead and use chromic acid. Because it doesn't matter in this case. And that would give me a faster reaction likely. Plus, it's the other one, so I can use both in the same problem. Look at that. Yeah. Both the ones I gave you examples since the last question, right? Good stuff. Okay. Let's look at some different oxidizing agents again. Has anybody ever heard of potassium permanganate? It was that purple solution you guys probably used back in Gen Chem. It's a very, very powerful oxidizing agent. This is actually what it looks like right here. This is the permanganate part. This part here is the potassium part, of course. And then this one's chromic acid right here. And so what you'll notice is that they have very, very high charges on that central metal. They have these resonance oxygen structures around them. And so they are incredibly powerful oxidizing agents. They're highly resonance stabilized, right? So pretty cool structures that you can do a lot of oxidations with. And so right here, we actually see an example of using potassium permanganate. Keep in mind that this is an extremely powerful oxidizing agent. So if you let this react under any conditions it wants to, you can oxidize everything down to almost the highest oxidation states. Okay? So right here, what do you notice about those reaction conditions? That's an ice bath, isn't it? Yeah, it's an ice bath, right? We're taking a little bit longer to do it, but it's an ice bath. And so we're doing this because we need to keep this very controlled. If we allow it too much energy, it's going to oxidize everything down. Okay? And so this is actually going to oxidize your secondary alcohol here to a ketone, 60% yield. But keep in mind, you have to keep it on ice. You have to keep it very cold. What would happen if we took a primary alcohol and let that potassium permanganate do its reaction while warm? Well, we would actually get carboxylic acid. By the way, we have to put the acid in to finish off this reaction and neutralize the OH here. That potassium hydroxide right there. If you don't put this in, you'll get the carboxylate. Okay, just the anion, right? So that's carboxylic acid that's oxidized down to almost its most oxidized state. Do you guys know what the next oxidation state after that is for carbon? It'd be CO2. Yeah, that's the furthest oxidized state. But you have to start breaking the carbon-carbon bonds, which is difficult. Okay. All right. Now, what we'll notice here is that potassium permanganate is not particularly selective, and it tends to oxidize things down very quickly, very effectively, but indiscriminately. The chromic acid is a little bit more discriminating. It's a little bit more selective than potassium chromate. So potassium chromate can actually oxidize compounds such as alcohols, aldehydes. It can actually oxidize down alkenes, alkynes, and alkyl benzenes as well. Whereas chromic acid is not going to react with alkenes, alkynes, and alkyl benzenes. And so you can use chromic acid in those cases rather than potassium permanganate. Let's go ahead and look at generating a Grignard reagent. You guys may remember this right here, for example. This is generating a Grignard reagent. In this case, we have a bromobenzene, right? And so we're going to put magnesium in the presence of THF. This is going to insert that magnesium and give us our Grignard reagent right here, which is like an analog for a negatively charged carbon, right? It's a very controlled one, though, and lower energy than some of the other forms that we've seen. This one's going to be an alkyl lithium reagent here. So we put lithium solid, lithium metal here. And this is going to be in diethyl ether. None of these are going to work with water. Water would just react away all of our metal and we'd be left with nothing, except for salt. Okay. And so this is actually going to be generating our alkyl lithium reagent. And we've seen that used many times before. Again, note that that's a quite powerful nucleophile, right? Again, these are pretty powerful nucleophiles. We can make something a little bit weaker. And so this is going to be generating our lithium alkyl group right here. And then what we do is we put it in with copper iodide under THF. And that's going to give us our lithium dialkyl cuprate. Notice what happens is that these join onto that copper here and give us the alkyl cuprate. And then we have the lithium as that extra electron source here. Note, you do actually generate lithium iodide salt, in case you're wondering. So do keep that in mind. You can separate these fairly easily because this is a lithium iodide salt. So it's not quite as soluble in most organic solvents. This is actually a transmetallation reaction. Trans meaning we're replacing, right? Metallation, the metal portion. Okay, some of those useful carbon-carbon bond coupling reactions that we've been looking at would be, for example, this is our alkyl cuprate right here. And we're targeting that positively charged carbon with a good leaving group on it in a very SN2 style reaction, right? Because it's an SN2 style reaction. Okay. Again, this is going to have excellent yield. Keep in mind that it's basically looking at that alkyl group and acting as if it has a slight negative charge to it, right? Now, the alkyl cuprates are excellent nucleophiles, but they're not quite as uncontrolled and reactive as like the lithium alkyl groups would be, right? So they have a little bit more control to them. The R group here, from the alkyl halide, this can be a methyl, this could be a primary, this could be a secondary alkyl group. It could actually be a vinyl or an aryl group as well. Vinylic meaning it has a double bond next to it. If it's an aryl group, it would be on a double benzene ring like structure, right? Okay. This dialkyl cuprate, these can be alkyl groups, vinylic groups, or aryl groups. So you can actually do this, for example, with something like this, where it's a benzene ring or something similar. So this actually opens up a huge number of different carbon groups you could assemble together into almost anything you want. These halogens here typically are going to be chloride, bromide, or iodide. Those are all excellent leaving groups. They'll give you slightly different rates of reaction, but they should all give you the reaction. This right here is an example, of course. This is the aryl one. So we're adding a methyl to an aryl here. And this is going to take 4 hours in diethyl ether, and we'll get 80% yield for our product here. This is vinylic halide. Again, this is the one off a double bond. And so we add, in this case, we're adding a benzene ring to it on the other side, which is that red group right there. And we get 90% yield after 2 hours in diethyl ether. Anybody have any questions there? Did I lose anybody? Okay. Okay, let's talk a bit about palladium catalyzed coupling reactions, or Suzuki reactions, and the Heck reaction as well. So this is the Suzuki coupling reaction right here. And again, you're going to be taking two R groups, two carbons, and coupling them together. In this case right here, we're going to have a boron-containing compound. This group here can be vinylic or aryl. It can't be anything like the previous examples, though. It can't be an alkyl group. It can be aryl or vinylic. This one right here, this can be an alkyl, this can be vinylic, or this can be aryl. Any of those will work here. This X here has to be chloride, bromide, or iodide. Any of those three, any of those halogens are good leaving groups, will work there. And this right here is your palladium right there. Anybody know what an L means on these things? Ligand. It can be any ligand you want. It just has to be restricted. Okay? So for example, that's that phosphorus with the 3 phenyls around it that you may notice from like the Wittig and all those things. Yeah. Fairly common bulky ligand that you attach to things. Okay. This can be in the presence of a base, so NaOH, and THF for our solvent. Note that our group here is actually going to retain the configuration. It's not going to have that configuration changed, so you can actually have an isomer that you specifically are targeting here and add on that arrangement. Okay, so this right here is going to be your mechanism. So the first thing we're going to have is this halogen alkyl group right here, and we're going to do an oxidative addition to it. This is going to involve that palladium with the ligand on it. Okay. So once we do the oxidative addition, it's going to attach to that R group, and the palladium will insert between the R group and the X. Notice it's very similar to as if you're generating a Grignard, right? Looks a lot alike. Okay. Can everybody see that similarity? You got your sort of Grignard reagent looking thing. Okay. So the next thing that's going to happen is your base, your OH minus, is going to do a substitution. And so that's then going to attack the palladium here. And your leaving group is going to leave. The next thing that's going to happen is you have to generate this boro portion to do the transmetallation. Again, because you have the OH in here, it's the exact same reaction conditions, so you can kind of add this whenever you want. Okay. What's going to happen is the OH is going to attack that boron right here. If anybody remembers, the boron only has 3 valence electrons. It tends to make that trigonal planar structure, right? And so what you end up getting is an empty p orbital that hangs out above it. And so these electrons actually attack there. This is going to cause this boron to have a negative charge. This negative charge is going to end up having the carbon being the bond that actually is going to leave here. The oxygens are going to be more electronegative, so they'll be harder to remove. And so this is actually the transmetallation right here, where we're going to get the R group attacking the palladium, and the OH is going to leave here. Transmetallation because we're actually transferring this metal bond right there. Okay. The next step is going to be we're going to have these two groups attach the palladium across it. And the next step is going to be an exchange where the electrons go from this R group here onto this R group here. So this, let's say it's an aryl group, something like that. We're going to attack that carbon. The electrons on this palladium bond are going to go onto palladium. This is one of the reasons you need the ligands, by the way, so they can pull electrons and keep those electrons in this structure. And this is going to end up being your reductive elimination. Notice, again, you're eliminating this group, and is a reductive elimination because you're reducing this by having a less electronegative electrons on it. And so we remove this, we regenerate our catalyst right here, which is the palladium with the ligands on it. And we can just do this over and over and over in cycles until we run out of our actual reactants. This actually is the Heck reaction. It's a very similar reaction. These two reactions together were grouped up, and their people were given a joint Nobel Prize, in case you're wondering. And so this is the Heck coupling reaction. We have an RX here. This can be vanillic or aryl. This right here can be a vanillic or aryl group, either one. The X again is going to be a Cl, Br, or I. And notice again we have a palladium with ligands in the presence of a base. Sound familiar enough? Okay. Okay. Yes, very, very, very familiar. Okay, so what's going to end up happening here is we're actually going to join at this hydrogen end right here. And that's going to be our big difference. Is our hydrogen end is the one that's actually going to join over here. So your bond is actually going to be between the hydrogen end of this double, or it can be an aromatic ring as well, and where this leaving group is. This will give you 81%. It will give you the trans configuration for this arrangement here. This side will actually retain the configuration, whatever the configuration used to be. It will always end up retaining that configuration. Let's go ahead and look at the mechanism here. So the first step of this is we're going to again get that oxidative addition with the palladium, the same as we saw before, where we're going to end up with that R group on the palladium with the ligand, and the X group across, very similar to a Grignard, right? Okay, the next step is then going to be directly an insertion of that double bond. So again, that's that double bond with the hydrogen over here. That's actually going to be attacked by this R group here, putting its electrons into that vanillic end. And then the double bond pi portion, the pi bond here, is going to get pulled into the palladium. An interesting side note that if you looked at this is actually a fairly typical ligand bond that you would make between a transition metal and a pi group. Has anybody ever seen phenyl in the presence of iron? Fairly common test used to determine if you have phenyl. That turns purple because the iron sits down on top, the phenyl group, the pi bonds, and attaches to them. That's too bad. Fairly common thing whenever you make like aspirin, if you made it in like gin chem. So the next part is going to be a beta hydride elimination. And so again, we have this structure right here where we have the substituent right there, and our double bond is currently not a double bond because we have the pi bond pulled into a bond here. And so what's going to end up happening is we'll get the electrons back into a pi bond here, and the hydrogen carbon electrons are going to move onto the palladium. Notice that's going to eliminate the hydrogen and have it leave with the palladium now, reestablishing our double bond. We actually need some form of base here to help us pull that hydrogen off and regenerate our catalyst. And so that's what this is going to do for us. It's actually going to act as a little bit of a base to pull that hydrogen off. And so it's going to give its electrons into a bond with the hydrogen. Hydrogen's going to leave its electrons on the palladium, and that's going to cause the halogen to leave with a negative charge. So then we regenerate our catalyst right here. If you don't have the presence of this base, by the way, this amide, that's the amide right there in that case, you only do one cycle of the reaction because you actually use up your catalyst. Okay. All right. So let's talk a bit about alkene metathesis. So this is going to be joining across an alkene where we can actually swap different groups across it. This can be using a Grubbs catalyst. So when we treat this with a Grubbs catalyst, this reaction is going to take 4 hours. What we'll actually see here is we will actually get where this reacts across and rearranges with this blue portion, which was one side of the alkene, doubling up here. And over here, we see the two red sides doubling up on this side. Everybody see that okay? And so notice the naming of it, literally a metathesis, meta swapping, right? Of these two sides for the alkene. This is actually considered a alkene metathesis, but the other name for it is an olefin metathesis. So you can actually also call it an olefin metathesis. This right here is actually what we're going to use to do this reaction. That's the Grubbs catalyst right here. Okay. Notice it's Ru with two ligands, and we have the chlorides right here. These two ligands can be a variety of different things. Typically, they're somewhat bulky groups. So the only important parts are this part right here that's in that planar configuration. Okay, so in this case right here, we're going to have terminal vinylic bonds. And so what we'll see here is these will actually join together, giving us the structure of the red part joined together by a double bond. And then these groups are going to be swapped over, and they'll get us our ethene. Ethene's a gas, so it's actually going to leave this, and that'll drive the reaction forward quite well, and so we will get 82% yield. Again, we have another example of them being terminal, but they're on the same group, right? The same carbon chain, okay? And so what we'll see here is this will actually be a ring closing reaction, making a double bond inside the ring. And so that is an intramolecular reaction. Cool, huh? So we got a ring closing metathesis. Lots and lots of options. Let's look at the mechanism now. So this is actually what the Grubbs catalyst does here. Right here's the metal portion of the Grubbs catalyst. This is the double bond portion. And then this is the CH-PH. Anybody know what pH is? You got it. Yep. That's a phenyl group, right? And so the next portion is we're then going to have an addition. So notice that we opened. We attacked here with the carbon, pi bond attacked the metal here. This pi bond went onto this carbon right here. The next portion, we'll have this four-membered ring. This is not particularly stable. And so we get a ring opening reaction for the next portion, where it just does a rearrangement, where this bond goes into the double bond here, and this one goes into the double bond here. Notice now we'll have our structure connected to our metal, won't we? This portion right here is going to be connected to the carbon with the phenyl. Note, by the way, does this necessarily have to open up like that? No, it could have opened the other way, right? In which case we would have gotten this. Okay? And so this right here is at equilibrium. It's going to just keep going back and forth, generating some of this species at any given time. Okay, so what's then going to happen is we'll have our new Grubbs catalyst, as it were, but now it has our functional group we actually want, doesn't it? Our R chain that we actually wanted. And so what's going to happen next is we're going to go ahead and react with one of the original alkenes. And this is going to be our addition reaction again, where we make that same ring structure. So again, the double bond with the metal goes on to that exposed carbon on this alkene. This one right here, the pi bond, is going to go on to this carbon, and we'll make our 4-membered ring. And again, we'll get a ring opening. Again, it can fall apart either direction. And this will generate our new alkene with this metal with the CH2. Note that these can drift around and then react the other direction. And so, to produce the ethene, the CH2 group has to be oriented at the same end as the metal, and the CH group, our group, has to be oriented the same end as the CH-PH. So if these collide together right here, what ends up happening is you have to orient the metal. So it's oriented with the this R group here. Okay. Excuse me, here. So metal up here, CH2 down here. That's going to give us our ethene. Okay. And it's the same reaction as here. So whenever you generate these, what you're really seeing is your grub catalyst basically just swaps over and over with any double bond. Okay? And you end up generating a bunch of these fragments. They're then going to start colliding together. And really your big difference here is that you have a limited amount of grub's catalyst, and so you only get a limited amount of that, whereas you have more of the original alkene. Okay? Now, this reaction is actually going to get helped driven forward by one factor in these cases here. Can anybody tell me why these would be especially easy to drive forward? No. Okay, how many carbons do you usually need on some sort of alkane for it not to be a gas? So methane, natural gas in your house, is it a gas or a liquid? It's a gas. How about ethane? 2 carbons. Let's skip that. Nobody knows that one as well. How about propane tanks? Gas or liquid? Gas or at atmospheric pressure, right? Butane? Yeah, it's actually a gas at atmospheric pressure, but it's easier to pressurize into a liquid. So you see those liquid inlighters, right? But when you flick them, it goes to gas, doesn't it? So do you think that's a gas or a liquid at room temperature, atmospheric pressure? Yeah. And so this actually really helps this move forward. It's because you can actually evolve this off as a gas, right? This is an equilibrium. And so if you continuously remove product, you're going to keep making more and more product, aren't you? Okay. Le Chatelier. Gotta love Le Chatelier. Okay, let's call that a day. I'll see you next time. We'll finish on the last chapter. And then we will be done.